Hello everyone, welcome back to part 3 of chapter 8, and we are continuing our discussions with conservation of energy, and if we can keep track of all the different types of energy in the system and keep the overall values equal to each other throughout the problem. So whether there's a change in velocity or a change in position, if we can keep track of all the different types of energy in the system, then we don't have to do work in the sense of what we had back in chapter 7. And that's kind of nice because the only way that we had to evaluate work done by forces was to use some vector math. But because energy is a scalar, we can just use scalar quantities and scalar expressions to do all of the physics for us. So that's our ultimate goal with this conservation of energy approach. And we're going to start off this video with a pretty basic example of the roller coaster. So I'm going to draw a roller coaster with a couple of hills, and then we'll have one really big hill towards the end there. Down here we'll have ground level. Zoom out just a little bit. And up here is where the roller coaster ride is going to start. So arms up. That's the way to ride any roller coaster. The initial height of this first hill we will call big H. And we're going to just barely nudge our way off of the top of this first hill. So we'll say that the initial velocity, or in this case, the initial speed, is 0. But then as we nudge our way off the side, gravity will grab hold. Gravity will start doing work. It will pull the cart down to the bottom of that first hill. And at that point, we should see a lot of the potential energy from our initial site converted into kinetic energy at the bottom of that hill. And what I want to know is when we get to the bottom of this hill, how fast is the cart going? Then the cart travels up to the top of the next hill, which is relatively shorter than what the first hill was. But when we get to the top of that hill, I want to know how fast is the cart moving. And we'll go ahead and say that the height of this hill and the one right next to it are both little h. But before we get to the next hill, we have to drop through the valley of those two hills. And then we go up to the top of the next one, and then down to the valley. And then at some point, our cart is going to travel up this very, 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 very long segment of track until it comes to a momentary halt at some point. Now, I don't know exactly where that is going to be, but maybe we can find out. So every one of these blue dots that I've drawn here, these are points of interest in the problem. And at any point of interest, I should be able to keep track of the energy that is present at those locations. Now I'm going to label each of these points just so we can keep them organized. We'll take the first point and we'll just call that E0, since that's the initial starting point. And then we'll just go right along labeling these as E1, E2, E3, E4, E5, and then up here I'll call this one E final, since that's the last one that we have in this example problem. And our conservation of energy description says that we have to have the same amount of energy at all times. And that means that the energy associated with all, what do we have here, 7 different points, they all have to equal each other. I can only compare 2 energies at a time, but we have so many choices now. Which energies do we want to compare to each other? Well, I could go chronologically, and I could compare the initial energy to the energy at site 1, and then I could compare energy at site 2 to energy at site 1, and just keep going. But there's nothing really chronological about this. I don't have to go from E0 to E1 to E2 to E3 with the math, the way that it's set up. If I wanted to, I could compare the energies at the initial and final points. I could compare the energy at E2 to E5 if I wanted. At this point, it should not matter. What matters is that I can only have 2 expressions in the equation at one time. Well, I want to know information about all of these different sites. And it would be best if we started with one of the sites that we actually know some information about. About the only thing that I do know is that our cart, which will have some mass of m, so that the cart and the rider will have some combined mass of m, has started at an initial height of h with an initial velocity of 0. So if I take the energy at the initial site and I try to fill in everything that we know about this. Now, compared to the previous example problem that we saw in the last video, there are no springs in this problem. So the only type of potential energy that I have to concern myself with is potential energy due to gravity. And I'm going to call this H0 because this needs to be the height above the 0 point that we are measuring for our potential energy. Now, as I just said, this is the height above the 0 point. Potential energy needs to have a 0 point labeled in the diagram. We need to know where the potential energy in the system is equal to 0. We can choose any location for that value, but choose a point that makes sense. I'm going to choose ground level because the cart and the rider should never drop below ground level as they're going through this roller coaster ride. And if I keep ground level as 0, then all of the potential energy values for the problem will be positive. All right, and then whatever initial kinetic energy we have at our initial site. So there's the expression that describes the energy at the initial location, but we can do a little better. Since we know the initial velocity is 0, the initial kinetic energy is going to be 0, and since we know that the initial height is now h above the 0 point, then we can call this mgh. All right, so there's E0. It's mgh. And we'd probably like some values for these, but we're going to hold off on that. because we want to put together some general expressions to tell us what the energies are at all of these other locations. Well, could we just take this equation and say that E1 equals mgh and E2 equals mgh and so on and so forth? Well, yes and no. Whatever this value turns out to be, whatever number this is, we can set that number equal to all of the other values. But it would be incorrect to say that the energy at site 1 is made up of potential energy, mgh. That's not the case. Instead, E1 should be made up entirely of kinetic energy. So let's see what we have for E1. We would have kinetic energy at site 1 plus potential energy at site 1, which would become 1/2 mv1 squared plus mg h1. Well, h1 is the height measured above the 0 point, but we're at the 0 point for potential energy when we get to the bottom of this first hill. So that's a 0, and that means that E1 has to have all of its energy in kinetic form. So what happens when we get to E2? E2 will have energy in the form of some kinetic and some potential. Those kinetic and potential values will be based on the speed and height at that location. Now, we really have no idea as to just how fast this cart is traveling when it gets to the top of this smaller hill. And so we don't want to make the mistake of saying that the velocity is 0. Okay, we don't know that for sure. And the reason we really don't want to make that mistake is because little h is smaller than big H. We are not going to recapture the total amount of potential energy when we get to the top of that smaller hill. And that means there has to be some energy left over, and that will have to be in the form of kinetic energy. So the best that we can do right now in describing the energy at site 2 is to say that we have some kinetic energy plus some potential energy, where H2 is being measured as H above the 0 point. Now you're probably thinking to yourself, well, we've got 1, 2, 3, we've got 4 more equations that we're going to have to write out here, but now is where things get pretty straightforward. If we look at the energy at location 3, well, how is location 3 any different from location 1? Well, we know that numerically they have to equal each other, but if I start filling in all the terms concerning location 3, location 3 is also at the 0 point for gravity, so there's no potential energy there, which means that all of the energy at site 3 has to be in kinetic form. And if the energy at site 1 has to equal the energy at site 3, let's put those equations together. And what happens? Well, we lose the halves, we lose the mass values, and it turns out that the speed at site 1 will have to equal the same speed at site 3. So at the bottom of each of these hills, we're going to have the same velocity. Well, is that going to be true for the bottom of the next hill, E5? Well, let's go ahead and we'll jump ahead to E5. We'll come back to E4 in a moment. But E5 will have energies based on the combination of kinetic and potential. But our height at position 5 is at the 0 point for potential energy. So our potential energy at site 5 goes to 0. Our energy at site 5 is all in the form of kinetic energy. And if we were to compare E5 to either E1 or E3, well, what we'll find out is that the speed at site 5 has to equal the speed at site 1, and we already know that the speed at site 1 has to equal the speed at site 3. But let's just carry through with our argument here. Yep, looks like the speed at site 5 also has to equal the speed at site 3. And this is because all three of those points, E1, E3, E5, they're all at the same vertical position. It just happens to have a 0 potential value. But if having these 3 points at the same vertical position means that they have to have the same speeds, then what might that mean for E2 and E4? Because they're both at the same vertical height. They're both using the same height of little h. Are they going to have the same speed values? Let's find out. We already have the expression for E2. Let's find the expression for E4. That's going to be K4 plus U4, which is 1/2 mv4 squared plus mgh4. So all I'm doing is writing out the equation with the appropriate subscripts, and now we'll look at filling in what we need. So E4 will have some kinetic energy based on the speed V4, and the potential energy, the height at position 4 is just the height little h. So I'm going to replace h4 with just that generic h. The energy at site 2 has to equal the energy at site 4. That's what our conservation of energy equation says. So if we set these two equal to each other, we have 1/2 mass V2 squared plus mgh has to equal 1/2 mass V4 squared plus mgh. Well, there it is. We have the same potential energy values at site 2 and site 4. And as far as our algebra is concerned, those can be canceled out. And we're left with setting the kinetic energies at the tops of those two smaller hills equal to each other. But the only way that that's going to happen is if the speeds are the same at the top of each of those hills. All right, well, I said that I wanted to know the speed at each of these locations, and now looks like our work is turning out to be pretty straightforward. I know that the initial speed at the initial location is 0. I know that the speed at sites 1, 3, 3 and 5 are all going to have to equal each other. so I only have to solve for one of those. I know that the velocities at sites 2 and 4 are going to equal each other, so I only have to solve for one of those. And what about the velocity at the final position? Where was our final position at? Well, it was way up here at the top of this last hill. And the reason that that was our final position was because that was going to be our maximum height. And if it's our maximum height, that means we don't go any higher. That means we have to momentarily stop. So there we go. That's our final velocity. All in all, I only have to solve for 2 different values. I can solve for any one of these, and I get the other 2 for free. I can solve for any one of these, and I get the other one for free. The last thing that I wanted to find was, what is that maximum height value going to be? So let's take a look at that. Let's take a look at the energy at that very last position, E final. At E final, we will have a combination of kinetic and potential energies. We just need to fill in the appropriate subscripts. Our final kinetic energy will be based on the final speed, and our final potential energy will be based on the final height. Well, we already know that at this maximum height, H final is going to equal the maximum height value that we're searching for. But if we're at max height, the final velocity has to be 0. So 0 kinetic energy. And there is the expression for the energy at the final location. Can we compare that to anything else that might be useful? Well, we've got all these different equations here along the way. Most of them are involving some kind of kinetic energy term, except, well, hey, what about this one? E naught. All of our energies have to equal each other. All of these energies have to equal each other. Well, there's nothing that says that I can't compare the initial and the final energies. And if I do that, my initial energy says I'm only in a potential energy form at the starting height of big H. So we have mg big H, whereas for the final energy, I have all potential energy in the form of mgh max. And it doesn't take much to see that the maximum height that this roller coaster is going to achieve at the far end is going to equal the initial height that the problem started with. So now I have h max. It's equal to the initial height. Well, look at how much we've been able to do just by sticking with the general solutions. We were given the initial velocity, and it was implied as to what the final velocity was. But from there, we were able to put together all of these different energy equations just by keeping track of how much of each type of energy we had at each of those locations. And we were able to come to some pretty neat outcomes. So now, as you're probably hoping, is he going to give us some numbers to work with? Sure, I'll give you a 200 kilogram cart, and that is the combined mass of the cart and the rider. We'll do a 25 meter initial height, and that's it. That's all you get. So is that enough to solve for all the other information that I wanted to know? Absolutely, because right here, that initial energy expression says all the energy in the system is in potential form, and all of that energy has to equal mgh. So mgh is mgh. Grab our calculator, plug that in, get an answer. 200 times 9.8 times 25 is 49,050 joules. That is how much energy is in the system. So every one of these energy terms, E0, E1, E2, E3, E4, E5, E final, these all equal 49,050 joules. Now that we know how much energy is in the system, we can go right down the line and solve for whatever is missing from each of these expressions. But keep in mind, of all of these equations, there's only two things that we really need to solve for. If I solve for V1 and V2, then I have everything else that I need, and we're done with the problem. But if you want to do a couple of self-checks along the way, if you want to make sure that E2 is equal to E4 by plugging in all the numbers and solving, you can do that. So E1 is all in kinetic form. E1 is 49,050 joules, and that has to equal half m1 v1 squared. So we solve for v1 squared. We need to multiply each side by 2, divide by the mass, which was 200, and then take a root. And I'm getting approximately 22.15 meters per second. That is the velocity when we get to the bottom of that first hill. So right here, we've got 22.15 meters per second. But that's also how fast we're going when we get to the bottom of the next hill and the next hill. All three of these are going to be 21.15. And that has already been established by comparing E1, E3, and E5. So these are all 22.15 meters per second. On to V2. So V2 is part of E2. We'll bring E2 down here. E2 is 1/2 mv2 squared plus mg little h. All of that has to equal the 49,050 joules. We're solving for V2, so we will start by subtracting the mgh term from each side. 4950 minus mgh. We then have to multiply everything by 2, divide everything by m, and then take a square root. And that will give us the speed at V2. Now, I don't think I gave a value for little h. Trying to get, okay. Nope, I did not give a value for little h. But it looks like little h might be about, I don't know, the way I've drawn it, it looks like it might be about a third. But let's say that little h is equal to 10 meters, just to keep the numbers reasonable. So little h is 10 meters. Plugging everything in to mass of 200, 49,050, 200, gravity, and little h. Calculator time. Let's see, 200 times 9.8 times 10. That's 19,620. We have to take the difference in that and the 49,050. Multiply that by 2, divide by 200. And we're going to have the square root of 294, which is 17.2 meters per second. So both V2 and V4 should be 17.2 meters per second. And we're done. We now know everything that there is to know about this roller coaster system. We know the velocity at each site, and because of that, we know what the kinetic energy associated with each of those locations is. Based on our choice of 0 point for gravity, we can now measure the height above that 0 point to give us the potential energy at any of those locations. And for any location, the combination of the kinetic and the potential energies for this particular problem is always equal to 49,050 joules. Now, it became fairly easy to solve for this once we knew what the energy of the system was. Once we knew that we had the 49,050 joules, we were good to go. But is it possible to find some of these values without actually needing to know how much energy is in the system? In other words, is it enough to know just that this is a system of points that all have to have the same energy? Do we really need a numerical value for the energy? Or can we get away with just comparing energies at 2 points? So for that, what I'm going to do is I am going to remove the mass from this discussion. And you might say, well, that's not good because every energy expression that I have depends on the mass. Well, say that again. Every energy expression depends on the mass. So what would happen if we took one energy expression and we set it equal to another energy expression? The first thing that we were ultimately trying to solve for, wanted the highlighter function. The first thing that we were ultimately trying to solve for was how fast is this cart moving when it gets to the bottom of that first hill. And we were able to find that. But we used the mass of the cart to do that. I'll let you keep the other figures. I'll let you keep the initial height of 25 meters. I'll let you keep the height of the two smaller hills and the initial velocity of 0. But let's just try comparing the first two equations to each other. Let's take the initial velocity of mgh and we'll compare it to the energy at the bottom of the first hill, which is 1/2 mv1 squared. Now that we see those two energies compared to each other, what's the first thing that jumps out to you? Well, they both have the same mass, and so the mass cancels out. I don't need to know the mass. Everything else in that expression, with the exception of V1, is a known value. We can use this to solve for V1. I need to multiply each side by 2 and then take a square root. But this should tell me the value of V1 without ever needing to know what the mass of that cart is. So these values will be plugged into our calculator. We have root of 2, 9.8, and 25. And that is square root of 490, or we get 22.15 again. So the point to be made by this is that in a lot of these energy equations, when we compare one energy to another energy, we're almost always going to have a situation where we have the same mass on both sides of the equality, and that mass is going to cancel out. This is kind of important for the roller coaster system, because if you put this roller coaster into operation and all the speeds at all the different locations, if they vary based off of the mass of the rider. Remember, our mass for this system, we had 200 kilograms up there, but we said that that 200 kilograms was the mass of the rider plus the mass of the cart. Well, the cart may maintain a consistent value for mass, but every time a new rider gets into that cart, you could go from a large adult to a small child, and that's going to have a pretty substantial change in the mass. Yet, as far as our energy equations state, the mass doesn't matter. Where did that go? Here we go. As far as these energy equations are concerned, the mass doesn't matter. Whether it's a small child on this ride or a large adult, when they get to the bottom of that first hill, they should both experience the same velocity at the bottom of that first hill. And they should all experience the same velocity at the top of the next hill. They should all experience the same velocity, all the way through. And this is also going to be important because we said that the final height that the rider and the cart can achieve, the maximum height, has to equal the initial height. If the velocities were changing based on the mass of the rider, you could very well have certain people that travel higher up than others. And if we don't have enough track, then you could end up with a lawsuit where somebody ends up going off. But everybody is going to maintain the same positions and the same speeds at all of these locations, regardless of their mass. So that makes for a much easier time in designing some of these roller coasters. So we said the maximum height was 25. Okay, so maybe you design this roller coaster so that you've got 26 meters worth of track in terms of height, and so those riders, they get right up real close to the edge, and you just scare the hell out of them thinking that they're going to fall off, but they never do because they don't have enough energy to continue traveling upward. Unless you gave them some additional energy at the beginning of the problem. What if we gave this cart an initial velocity of 2 meters per second? How would that affect things? Well, it would definitely affect all the values as we go through. Starting with a higher amount of kinetic energy is going to mean that we have a higher amount of energy available at all points in the problem. We can just as easily go through and solve for what those are going to be, but that's going to take up some time. What I want to know is if we increase the initial kinetic energy of the system, what would the new maximum height be? So we'll get rid of some of this stuff here so that I've got some room to work. And remember, we can compare energies at any two sites in the problem that we want. I want to compare the initial energy to the final energy. The initial energy now has an initial amount of kinetic energy plus the initial potential energy. The final energy of the system, so now we're expecting to go to a slightly higher final height, but we can still argue the fact that the final kinetic energy still needs to be 0. The only way that we can achieve a maximum height is if we stop moving up. Let's solve. Well, everything has a mass in it. Where's the mass? You don't need it because everything has the mass in it. The mass cancels out. So it shouldn't matter what the mass of the rider and the cart is. What matters is what is that initial velocity and how is it going to affect the final height of the cart. So we'll put some numbers in for all of this, rearrange some stuff. Now, is the energy in the system still 49,050? And that answer is no, it's not. The reason it's not is because we have added some additional kinetic energy to the system. Another reason we don't want to make this mistake of using this number is because we're no longer utilizing the mass in this problem. And that 49,050 joules, that was the energy associated with all of these terms, and all of these terms did involve the mass. If you change the mass of the rider, you change the energy of the system. But that energy still has to be conserved at all points. Hence the reason why we went through and we used all general expressions. But back to the new maximum height. What will the new maximum height be? Well, the only thing we have to do is divide both sides of the equation by gravity, and we'll have our answer. So 1/2 V0 squared divided by G plus GH divided by G is just going to be H. There's our answer. We have half of V0 squared, 2 squared, 9.8, plus h, that was the initial starting height of 25 meters. This will tell us what the final maximum height is. I have a 2 down here. There are 2 2's in the numerator, so just 1 will remain. 2 divided by 9.8, that's not a whole lot. That is 0.2, or that would be the equivalent of 20 centimeters. So the new max height would be 25.2 meters. Not a whole lot. But again, the great thing about this is that we don't need to worry ourselves about the mass of the riders. If we give each cart an initial velocity of 2 meters per second, every cart will achieve a maximum height of 25.2 meters, regardless of who is riding in that cart. Now, at this point, you might be asking yourself, well, we didn't take into consideration any friction. And you are correct. We did not. In the previous video, we brought up the idea of friction in these conservation of energy systems. And so what we're going to have to do in the next video is we need to figure out how we're going to incorporate friction into these systems. If we do a quick example problem of a mass sliding across the tabletop, let's give this mass an initial velocity of 5 meters per second, and it's going to slide over the tabletop until it comes to a halt. So V final is 0. We're sliding over a flat horizontal tabletop. So what does that mean in terms of any changes in potential energy for the system? There are no springs, so we don't have to worry about spring potential. That means we only have to worry about gravity potential. But the height at the initial location is the same as the height at the final location. So what happens when I have two of the same terms on either side of the equation? Well, they're equal, and so they're going to cancel out. Another way that I could argue that is I could just say I want ground level to be the 0 point for gravity potential. And that means that both of these terms would be 0, and so they still cancel out. The only thing left in my equation says that the kinetic energy must now equal the final kinetic energy. But how do I take kinetic energy with initial velocity 5 meters per second and get that to equal kinetic energy of velocity 0 meters per second? That's not possible. That can't happen. In other words, I am not able to conserve the energy of the system given this equation. And that's because this equation is incomplete. We're going to have to add some stuff to it. Eraser. The way that the equation is written right now, this is what we call the conservation of mechanical energy. And mechanical energy is not a new kind of energy that we have to learn. It's not something that we're going to include into the equation. Mechanical energy is just the combination of the two energies that we've been using this whole time. And if we can conserve the value of this combination, then we say that we have a conservation of mechanical energy. And mechanical energy is the good kind of energy. This is the energy that we use to move things around, to do work. You know, we have to pick something up and move it to another location. Well, that involves changing potential energies, changing kinetic energies. And so that's the good kind of energy. That's the stuff that we're able to use in industry and make products and ship products. You know, it's what keeps our society going, basically. But in this case, we started with some amount of energy in the amount of kinetic. If we want to give a mass to this, we could say the mass is 2. And so our initial kinetic energy would have been 25 joules. If we want to let the potential be 0 at ground level, that means we had 0 potential to start with. But then we come to a halt after sliding over this friction zone. We no longer have any kinetic energy, and we don't have any potential energy, and this is not right. That is not correct. If we started with 25 joules of energy over here, we have to have 25 joules of energy over here. The only way that's going to happen is if we include another form of energy into our discussion. And that energy is what we are going to call thermal energy. So there will be some change in thermal energy for the system. And this change in energy is the result of friction. As the box slides across the ground, friction is going to generate some heat. And that heat is going to dissipate into the system. Now, that doesn't mean that the energy is destroyed. The energy is still in the system. It's just not in a very usable form. Heat is sort of the bottom level of energy in terms of usable states. And if you've ever seen any kind of mechanical system, one of the biggest byproducts of any kind of moving system is that you're going to be generating heat. And heat means a loss of mechanical energy. But now we actually have a means of balancing our conservation of energy equation. The only way to make this work is if we've generated 25 joules worth of thermal energy. And so our new and improved conservation of energy equation, assuming that we do have real-world situations like friction, air resistance, drag, we'll need to take that into consideration. And so this is the conservation of energy equation that we are going to continue with into the next video. We'll look at a couple of example problems involving friction and see how friction ultimately makes our lives more complicated. But until then, have a good one.